In 1927, one equation proved you can never know a particle's position and momentum simultaneously. Heisenberg's uncertainty principle, published that year, shattered 200 years of Newtonian clockwork physics. But this means your own atoms are fundamentally unpredictable right now inside your body. Werner Heisenberg, suffering from hay fever on Heligoland, his work killed certainty, replacing a predictable universe with one ruled by probability and limits. It was merely a question of building better instruments, better telescopes, sharper microscopes, faster detectors. The limits were technological, not fundamental. Laplace had imagined a demon that could know every particle's state. Classical physics had no room for mystery. Heisenberg's breakthrough on that barren North Sea island. He was working on a new mathematical framework called matrix mechanics, trying to describe the behavior of electrons inside atoms. When he calculated the position of a particle, the momentum became fuzzy. It was not a flaw in his math. The principle he formulated was devastatingly simple. The more precisely you measure a particle's position, the less precisely you can know its momentum. You cannot beat that number. No matter how clever your instrument, no matter how powerful your laser. Heisenberg imagined trying to measure an electron's position with a gamma-ray microscope. But a photon carries momentum. The shorter the wavelength, the more accurate the position measurement, but the more energy the photon carries. You cannot observe without disturbing. The act of measurement itself creates the uncertainty. This was not a minor technical annoyance. It was an existential threat to causality. If you cannot know both where a particle is and where it is going, you cannot predict where it will be tomorrow. Einstein hated this. God does not play dice. But the mathematics was ruthless. 4 landmark experiments would drive this impossible conclusion deeper into the fabric of reality. A simple laser and a single slit, the double-slit electron detector, and finally a trapped ion in Sydney, vibrating in a vacuum chamber. Each experiment asks the same question. Is this limit a flaw in our instruments, or a fundamental law of the universe? The first experiment is so simple you could replicate it in a high school physics lab. A helium neon laser, an optical bench, a single adjustable slit, its jaws capable of closing down to a few hundredths of a millimeter. This is the standard undergraduate verification of Heisenberg's principle, performed at MIT at the University of Sydney. You shine the laser through the wide-open slit. On the screen behind it, you see a clean, tight spot of red light, exactly where classical physics predicts it should be. The photon's horizontal position is relatively unconstrained, so its horizontal momentum is well defined. Then you turn the micrometer screw and begin closing the slit. The spot on the screen does not simply get smaller, as you might expect from a classical particle. It begins to spread. The tighter you close the slit, the more precisely you localize the photon's horizontal position. New fringes appear on either side, dimmer bands of light marching outward. By the time the slit is barely a hair's width open, Professor Walter Lewin demonstrated this in his legendary Mittite lecture, the one that has been watched millions of times on YouTube. The students gasp. It is not a subtle effect. It is dramatic, instantaneous, and undeniable. The more precisely you constrain where the photon can be, the quantitative relationship is ruthless. The product of the position uncertainty uncertainty, call it delta x. That number is roughly 5.27 times 10 to the minus 35 joule-seconds. No matter how precisely you machine the slit, no matter how stable your laser, no matter how vibration-free your optical table, it is a law written into the geometry of reality. This is the first paradox. In classical physics, precision is always a virtue. The more carefully you measure something, but here, making the measurement more precise, narrowing the slit, actually makes the outcome less predictable. The act of constraining one variable forces the conjugate variable to become wilder. Minute physics creator Henry offered a clean explanation for this. It is a necessary consequence of wave behavior. This is true for water waves, sound waves, light waves. The slit diffracts the wave, and diffraction is simply the wave obeying its nature. So perhaps there is no mystery here, just waves doing what waves do. If the photon is a wave, what is waving? And if it is a particle, the single-slit experiment does not answer this. It only demonstrates that the boundary between wave and particle is not a boundary at all. But Heisenberg knew his thought experiment needed a real adversary. He imagined a gamma-ray microscope. The logic seemed airtight. To resolve the position of an electron, gamma rays have the shortest wavelengths in the electromagnetic spectrum. Fire a gamma-ray photon at the electron, catch the reflection, and you know exactly where it was. A gamma-ray photon carries enormous momentum, far more than visible light. The electron recoils like a billiard ball hit by a cannonball. You now know where the electron was at the moment of impact. The more precisely you measure the position, the more violently you disturb the momentum. The photon is the messenger, and the messenger is the disturbance. Heisenberg formalized this with a single equation that would become the bedrock of quantum mechanics. In plain language, the order of measurement matters, measuring position first, then momentum. This non-commutative algebra was not a mathematical curiosity. The universe does not allow you to know everything at once. Albert Einstein read Heisenberg's paper and felt the ground shift beneath his feet. In 1927, Einstein proposed a counter-thought experiment designed to break the principle. Behind the slit is a movable wall, mounted on springs. When the particle passes through, by measuring the recoil of the wall, Einstein argued you could determine the particle's momentum without ever disturbing the particle itself. Niels Bohr, Heisenberg's mentor and intellectual father figure, spent a sleepless night before the next session. To measure the recoil of the wall, Bohr pointed out, you need to know the wall's position at the moment of impact. According to Einstein's own theory of general relativity, measuring the wall's position relative to the gravitational field, Einstein had been defeated by his own theory. God does not play dice, he wrote to Max Born in December 1926, months before Heisenberg's formal publication. Bohr's reply was sharper. Einstein, stop telling God what to do. The two men debated for years. Einstein proposed thought experiment after thought experiment. Bohr dismantled each one, always using Einstein's own physics against him. The philosophical rupture was complete. Classical causality, the chain of cause and effect that had governed physics since Newton was dead. In its place stood a universe of probabilities, where measurement itself creates the reality it observes. It was a permanent feature of the cosmos, as fundamental as the speed of light. You cannot measure both. And that is not a flaw in your equipment. That is the universe telling you that some knowledge is forbidden. The third experiment takes us to the heart of the quantum mystery. Fire electrons one by one at a barrier with two parallel slits, and over time, they build an interference pattern on the detector screen. This is wave behavior, unmistakably. Each electron, it seems, passes through both slits simultaneously, interfering with itself on the way to the screen. But here is where the trouble begins. Place a detector at one slit, a light source, and a photomultiplier tube designed to catch the flash of a photon bouncing off the electron as it passes. Now you know which slit each electron took. The moment you turn on the detector, the bright and dark bands disappear, replaced by a simple blob, the pattern you would expect from classical particles fired through a single slit. The act of measurement collapses the wave function. Heisenberg used this exact scenario to explain the uncertainty principle in action. To detect which slit the electron passed through, you must shine a photon at it. It collides with the electron and changes its velocity by an amount inversely proportional to the accuracy of your position measurement. The disturbance is unavoidable. The interference pattern disappears not because the electron is shy. For decades, this was the settled view. Measure the path. It seemed airtight. But in the 1990s, a group of eminent quantum physicists claimed they had found a loophole. They argued that it might be possible to determine which slit a particle went through without significantly disturbing its velocity. The idea was to use a gentler measurement. If true, this would undermine Heisenberg's original explanation. The uncertainty principle might be real. The claim sent a tremor through the physics community. If you could know the path without disturbing the particle, it was something deeper. Perhaps a fundamental refusal of the quantum world to reveal its secrets without changing them. Was the uncertainty principle a statement about measurement or a statement about reality itself? Physicists designed a double-slit apparatus with an exquisitely sensitive detector, not a crude photon blast, but a weak measurement that barely touched the particle. The results were devastating to the 1990s claim. It persisted for up to 5 meters beyond the detector. The perturbation from measurement is not a local jolt at the moment of contact. It propagates with the particle. You cannot simply wait out the disturbance. The uncertainty is not a temporary inconvenience. It is a permanent scar that the particle carries forward in time. The act of measurement changes the system, and that change cannot be undone or subtracted out. Measurement at the quantum scale is not a passive observation. To see something is to change it, and the change is irreversible. Every observation leaves a mark, and that mark propagates forward, corrupting the very information you sought to preserve. There is only the participant, forever entangled with the system they study. The fourth experiment begins not with a laser or a slit. It is 2023, nearly a century after Heisenberg's hay fever scribbles on Heligoland, and the question has not changed. Ting Rai Tan and Christoph Wallahu led a team that constructed what they called modular position and modular momentum operators. In quantum mechanics, commuting operators can be measured simultaneously with arbitrary precision. The trick is that the modular operators sacrifice information about the total value of a variable to gain precision on its fine structure. If you look at the hand, you know the hour roughly, but you have no idea what minute it is. Now imagine you redesign the clock. You lose all information about what hour it is, but you can now read the minute with extraordinary precision. The modular operators work the same way. By discarding the coarse position of the trapped ion, the trapped ion itself is a marvel of engineering. It is held in place by electric fields. The ion vibrates at a specific frequency, and those vibrations are exquisitely sensitive to external forces. The team measured the ion's motion with a sensitivity of approximately 14 times 10 to the minus 24 newtons per square root of hertz. To put that in perspective, this sensor can detect a force equivalent to the weight of a single bacterium divided by a billion. They aim to push the sensitivity to 10 to the minus 27 newtons. At that level, the trapped ion could detect the passage of dark matter particles. The uncertainty principle, once seen as a barrier, has become a resource. By redistributing uncertainty, and that is when the real scientific puzzle emerged, one that still has no answer. The 4 experiments, spanning from 1927 to 2024, measurement is not a window onto reality. The universe sets the terms, and we cannot renegotiate. The single slit, the gamma-ray microscope, the double-slit detector, and the trapped ion, each one demonstrates that the act of observing is an act. You cannot extract information without leaving a trace. The question that keeps physicists awake at 3 a.m. is no longer, can we measure everything? We now know the answer is no. The question is deeper. Does the electron exist in a definite position before the slit determines where it can be? Or does reality only crystallize into existence at the moment of observation? It only guarantees that the mystery is permanent. There is a limit to what we can know. It is a law written into the fabric of space-time itself. The universe is not only stranger than we suppose, it is stranger than we can suppose. And the only honest response is to keep asking, keep measuring,